Okay, so from here, since you discussed this, if you follow this link, you can see how other people have uh, gone in to answer the question. And a couple of people have done a really nice job explaining it in the way that you all just talked through with that five data point example. And so here's a person and they simulated random data. They just made up random points on a Y and random points and called it an X. Here's the unsorted relationship. And then here's the sorted relationship. And if you think about each point as being representative of a person, one of the groups I was in was talking pretty quickly about how, each one of these points represents a human being. Who was that? You want to talk about that a little bit? I think that was
I think that
Sarah?
was our group.
Mm-hmm.
So the example that we were using, if you were thinking about like college admissions, the data points that like a admissions review board might look at, which might be your age, ACT score, maybe like an essay score, GPA, those things. So if those got separated from one another and resorted, that essentially would not represent you at all.
Yeah, no longer does this point represent Brandon. It doesn't represent Ari. It represents no one. It's just a point of somebody's score that's unconnected to a person anymore. And regression really ultimately is the study of relations among constructs within and between people. Okay, so bad idea. Don't do it. Have fun pouring through those. And you can look through the discussion board. If you haven't posted yet, go ahead. I've left it open for the next week, so you can go in and respond on there all you like. So what we just talked about is an example of an assumption of regression. It is, let's see, I'm reminding myself to record. Can you see this? Is this on? Am I sharing my screen? Oh, good. So this is one example of an assumption of regression. One assumption is that the data points that you have collected are all collected on the same person. Everybody in that row is one person or one place or one thing. Some sort of noun has been measured in multiple ways on multiple variables. And you're looking at how those are related. And the first thing I'm going to do is I'm going to talk to you about the math behind how this works, because I think it's important for you to understand when things go wrong, why they go wrong. So we are in scaffolding territory because there's going to be some equations. But I'm presenting it in a way that I think you'll latch onto fairly easily, reminding you in the way we've talked about this in the past. So if you remember this thing here that we've done before, that in regression, the whole goal is to get an expected or estimated score on Y for every single person, place, or thing that you measure. Now, the line represents our expected score. That's the Y hat. But our observed scores can be anywhere, any distance from the line. Each row is a person or a place or a thing. Now, remember our residuals, that's our error, how far away our points are from the line. And these are important because the whole point of regression is to reduce the amount of error. And the way that we get this predicted line is by minimizing that error. Do you remember we talked about minimizing the sums of the squared errors back in like week 3? You're taking the errors of each of these things and you're summing them or squaring them and summing them. So we always want in any regression equation to get this line, the predicted score should always be as close as possible to the actual scores or observed scores. Our average error between predicted and actual scores should always be 0, meaning we're not consistently overestimating everyone or underestimating everyone. I think I did that backwards. Overestimating everyone or underestimating everyone. Yeah. And then the squared difference between the actual and predicted scores should be at a minimum. That's the minimizing your sums of squared errors. That's what that is. Now, what I want us to think through next is one of the most, I think, easiest to understand violations of regression assumptions, other than the one we just talked about, which is if you separate the points from the people, then regression is now meaningless. The next most easy assumption violation to understand is outlying data points. So if I have this outlying data point here that's sort of outside of this relationship of the rest of these points, what does it do to this regression line? It will, that was a rhetorical question because I'm going to show you. It's going to pull this regression line down. Because in order to minimize the squared errors, we have to minimize this giant residual that this point will have from the line. So to minimize that, the regression line is going to be affected. The estimate would be affected. I'll show you a little bit more about that. That's basically the whole thing that this lecture is about. So to explain why it would happen, I want to go back to these equations. Do you remember the z-scores for y and the z-score for x? That's what this represents here. This is the relationship between y and x. It's the correlation multiplied by the z-score for x to get the predicted hat for y. So that zx represents the z-score of the x, which if you remember from week 2, we calculated, and it's based on this equation here. Each person's observed x for each person j, minus the mean of all x's, which is this, divided by the standard deviation of the x's. Stick with me. I promise we're going to get there. We can do the same thing for y. This is, again, each person's observed y, the mean of all y's, and the standard deviation of y. Now I'm going to do some algebra. And I'm going to move some products around to get our predicted y, our y hat, which is equal to this right here, this equation. So we have the mean of y is still here. You have x for this particular person, and you have x bar, the mean of all x's. And we've got our 2 standard deviations. So there's a lot going on here when we're looking at our predicted y's. So think about this equation here. This time I am asking you to participate. And I want you to think about, and maybe write to me privately in the chat, which values here on the right side of the equation are going to change when I add this point down here. What's going to change if I add this point on x? I'm seeing a lot of good results. So you're probably, what I'm seeing here, and I agree with, is that if you add a point, everything will change, just about. The mean of y is going to change because you added another point. This is within the scope of what y is, so it's not dramatically different. I didn't add a value of 100, so it won't dramatically change the mean of y, but it will change it. It'll change the mean of x because I've added another x point. The standard deviations will change. Probably the biggest change here, I mean, the standard deviation of x will change, the standard deviation of y will change, but the biggest change is probably this correlation, which is what the sort of line I just drew. Without that here, that line is pretty consistently like right among these points. When I added this, the correlation is going to go down pretty dramatically. I'll demonstrate that so to prove that I'm not just making it up. So why does this matter? Well, it matters because our estimate's no longer accurate, but it also matters for our statistical significance. So to test whether a coefficient is significantly different from 0, we look to this t-test estimate, which, if you remember from early on, we get the t-test by dividing the estimate by the standard error. And the standard error is derived from the total error in the model. Let me remind you how that works. You'll sometimes see mean squared error, which represents the average squared error in the model. And those error terms, they also have a variance. So the standard error of the estimate is the standard deviation of the residuals. So it's the standard deviation of all your errors. If you're really close to your estimate, then your standard deviation of your errors is really small because everybody has a very similar error. If you're not doing as good a job at predicting your observations, then those standard error of the estimate is going to be really big because some will be really large and some will be really small. That's the standard error of the estimate. Now, the standard error of the estimate is also sometimes called the root mean squared error. So I give you this notation because in the textbook, it's called the root mean squared error, but in SPSS, it's called the standard error of the estimate. So the standard error of a coefficient is calculated as the proportion of the standard error of the estimate that's associated with a specific coefficient. This is the formula that you use to do that. And if you would like to, I can follow you around here and you can see that all of this math works out. That's why I have all of this here. Here's the standard error of the estimate. This is being the total error in the model, which is why it's provided here along with the r squared. And then we're going to get the n here, which is this 15. The standard deviation, 7.5. Standard deviation of x is 7.5. And total, that's works out to 13, about 0.13, 0.14. So that's where the standard error comes from. It's this proportion of the error variance that's attributable to this particular variable we've added into the model. So now, another like 3 minutes of silence. Well, I want you to look at this equation and think about, I'm going to do more than 3 minutes. I'm going to do 4 minutes of silence. Well, I want you to look at and think about this equation and what would increase or decrease to give you a big standard error of the estimate. What standard error, how are you going to get a big standard error? And you can think, and then after 4 minutes, I'm going to ask you to type it into the chat. Okay, everyone grab your reaction tokens, your thumbs up and thumbs down reaction things. Do you have access to those? Okay. If I increase the RMSE, my standard error is going to go up, or are they going to go down? I see several thumbs up and several I don't knows. I saw somebody answer. Michelle, tell us why will the standard error go up if the RMSE goes up?
So doing basically just doing some quick math, you're increasing the numerator, dividing by a smaller number, so it should be a larger number.
As the numerator goes up, the size of the answer of the equation will go up. And Krista, what about decreasing or increase? What happens if you increase the standard deviation of x?
So the opposite of what Michelle said, essentially, by it's a numerator, that's the denominator. Shout out to Algebra 1 back in. But if you increase that number, that's increasing the number you're dividing the numerator by, which would decrease the standard error.
Yeah, exactly. So if I have a big standard error, is it going to be easier or harder to detect statistical significance? That's not to Krista, that's to the whole class. So if I have a bigger standard error, I have a less precise estimate. So it's going to be much harder to detect statistical significance. That's also, we're getting in the realm of statistical power. If you've ever heard of power. So if I want to have a better chance of detecting statistical significance if it exists, do I want more people or fewer people? More people or fewer people? More. I want to increase the size of this denominator so that this will be smaller. How can you make this bigger? What's going to have a more of a standard deviation? If I sample all intro stats students, or if I sample a random 100 people at the gas station, where am I going to see a bigger standard deviation? Probably at the gas station, the more random sample. So when you're thinking about we don't talk about sampling in this class directly, but this is a way I'm drawing your attention to the way you design your research studies, where you decide to get your sample, the kinds of measures that you give. All of that plays into your ability to detect statistical significance and your ability to get accurate estimates within your actual analyses that you do. Okay. That's all the math. I mean, there's still math. There's math in everything we do, but there's a lot fewer equations. We're going to be out of the scaffolding zone now as I move into part 2. More about statistical inference. So for these to be valid, the variables need to meet specific assumptions. Here are the 5 big assumptions of linear regression. The mean of the errors is 0. The predictors should be measured without error. Believe it or not, we expect that the predictors are measured without error. Any error, that's the distance away, right? The variance. Hi. The error is the distance of the point from the line. That's our error, our residuals. Those residuals should be independent for all observations. The variance of the errors is constant for all values, and the errors are normally distributed. I'm going to go through these one by one, so don't despair. Whoops. Now, the mean of the errors being 0 is not really a big problem because by design, regression is set up so that the mean of the errors is 0. Remember how we sum the squared errors and we're always never underestimating or never consistently overestimating or underestimating everyone, meaning the mean of the errors is always 0. So we're going to skip that one. But before we get to the rest, I just want to tell you what's at stake here. If you're violating these assumptions, what would happen? How bad is this? Like what's the big deal? If you have more errors, if you violate more assumptions, you're more likely to have more error in your estimates. More error means you have bigger standard errors, which means you're going to have wider confidence intervals, which means you're going to be less likely to see a significant effect. Generally, there are instances where outliers will do the opposite, but generally, this is what will happen. So that's why we want to check some of these things, these assumptions within the regression models, because you're slightly less likely to see significant effects than you might be otherwise. That might actually be there. So that's committing that type 2 error. Okay, so this first one we're going to talk about is that predictors are measured without error. Let's talk a little bit about that. Regression in and of itself is based on this idea of classical test theory. Classical test theory essentially breaks down to anything that you want to measure can be measured and has a true value. But everything that will be measured is going to be measured with some error. The difference between the measurement and the true value is called measurement error. Now, everything is measured with error, even if you're measuring how big your desk is. If you measure your desk, you're going to be off by some, always, if you get small enough and within enough detail. So this is not an achievable, we will always violate this to some extent, particularly those of us working in the social sciences. So if you have measurement error, generally your coefficients are going to be underestimated because of the way that the error gets distributed across your estimates. Now, the bias is directly proportional to the reliability of your predictor. Pointing out here that regression doesn't care about whether your dependent variable has error. They're fine with that. Now, theoretically, the way that this works is that your sample B weight is equal to the population B weight times reliability. So if your X variable, whatever it is, has a reliability of 0.7, there's a 30% underestimation of the sample B weight. That's how that works out. So if you've ever wondered, why do I have to report the reliability of my measures in this manuscript? Or why, when I'm reading this manuscript, is this person talking about how reliable their measures are? This is one of the reasons. Is because we do assume that there's no measurement error when we're running a regression. So what do I do? We will never be able to eliminate error, but we can minimize it. So you want to try to use as reliable of a measure as you can when you're using regression. You can also move into the structural equation modeling framework, which is there's a course offered next semester, maybe every fall. I don't know when it's offered. It's offered at some point, and it's on structural equation modeling. Any questions about measurement error? Do you want me to, who teaches the structural equation modeling course? I believe that's taught by, oh my gosh, Dr. Kim teaches that class. Thanks, Susan. I was like, it's Min Jung. What's her last name? Dr. Kim teaches that course. Okay, that's measurement errors. The next violation is a violation of independence of observations. That means that there's no relationship among the residuals of any subset of cases. If you pull a random sample from this population, you're going to meet this assumption. If it's a totally random population, sample from the entire population, you will meet this assumption. The assumption will not be met if the data are clustered. What does that mean? That means you have, for example, several students from each of 5 classrooms. If you're measuring something like how satisfied they are with school, it's likely that kids from the same classroom are going to rate their experiences more similarly to one another than kids in different classrooms would, because of the shared experience they have in that classroom. The same is true for patients receiving care, reviving care? I should say receiving care, in 3 different hospitals, or therapy being issued to multiple patients by 10 different counselors. In each of these situations, you have non-independent errors because people's experiences are based on their, people's data are going to be based in their experiences. So all of you have a very different experience this year in this regression class than my class did last year. Even though your teacher's the same, the year is extremely different. For one, we didn't know we could smell ants last year, and now we do. Maybe that has completely changed our understanding of statistics. What about students at several schools? So if you draw all of your students from one school, then you haven't necessarily violated the error of independence if you're talking about their school experience, but you might be because they're probably in different classrooms. So there are ways to measure just how much of the variance, the error variance, is attributable to differences between, say, classrooms or schools, and you learn about that in hierarchical linear modeling class, which we'll offer in the spring. Probably. That's also taught by Dr. Kim. Or sometimes it's taught by Dr. O'Connell. They both teach it. Now, what it does is increase your type 1 error rate. It's when you think there's an effect, but one is not really there. Sometimes. Dr. Kim this spring. Oh, good. Not that just good to have that information. So this is particularly violated if you're looking at something like how characteristics of teachers are related to students. Because if I measured characteristics of like statistics knowledge, if I want to know all about your statistics knowledge, and I'm looking at characteristics of the teacher, all of you have me as the teacher right now, which means that if I had a data set and I'm putting in something like the number of years of experience that your teacher has, it will be repeated multiple times, one for each of you. So it looks like the data are much more precise than they actually are, which is where this violation becomes a problem. Now, the next one I want to talk about is that the error variance in Y is constant. And now I get to say my most favorite statistics word. Heteroskedasticity. I know. My 13-year-old just said, what? Really, what did you just say? The heteroskedasticity represents it's the strength of the relation between the independent and dependent variable, and when it depends on the level of the independent variable. That is a whole lot of words to show you what that looks like. Don't even read that. I'm just going to show you. Look at this. This is a heteroskedastic relationship. You see that it kind of looks like a wine glass on its side, maybe. Speaking of bringing people joy. So there's more variance at this end, and there's less variance at this end. That's all it means. Regression doesn't do a great job of capturing this relationship because regression doesn't talk very much about variance. So this is pretty cool. How cool is it that the variance is different at this end than it is at this end? That might be really important and interesting. Regression does not give you an indicator of that. Okay. So this one is not the end of the world. You're not going to draw extremely wrong conclusions if your data look like this, but there's other important information that you might not be getting at. What can I do to make sure that this isn't a problem? What you can do is look at your relations in a scatter plot to make sure that those don't exist, and then be thoughtful about what you examine, because if you expect that that variance might depend on X or Y, you might want to measure it in a slightly different way. The other thing you can do, and you can do with any of these, is if you violated these assumptions, you need to talk about it in the discussion sections of your papers. So if you have done your whole experiment, done your whole analysis, and then at the end, right now, because this is where you are right now, you all have all finished up your assignments. If you go and you run some of these diagnostics that we'll talk about later, and you see that your data look like this, you have a heteroskedastic relationship, you can say in your conclusion sections, we see that this result is heteroskedastic, therefore we have to take these results, interpreting them with caution. That's all you can do. And we need more analysis and more data on this to draw better conclusions. Okay, here is the penultimate one, I think, which is errors are normally distributed. This is the error term. The error should be normally distributed. That's what's left over after you're done. Now, error is independent of X, which means the errors have no correlation with X. Sometimes this is called the third variable problem. If you have a third variable, something like Z, which is correlated with the X and Y, but is not included in your analysis, then the variance with it is going to be captured in the error term, which means that your error and your X will be correlated. When the same thing can happen if you use irrelevant variables, though that's much less likely. I included that because it's in your textbook. So let's talk about what this looks like. Sometimes this can happen if you have a curvilinear relationship and you try to fit a straight line to it. The relationship with X with Y changes across levels of X. What's this? This is a growth chart. And if you try to fit a straight line, you're going to have more variance at one end than the other. This is still heteroskedasticity, basically. Sometimes this can come up if you're looking at something that has a restriction of range. So for example, if you study kids who are gifted at math or employees who have low morale, you might have data that look like this. And you might have heard you can't use regression if you have skewed data. That is actually not true, because we only have an assumption about the errors. We do not have any assumptions about the distributions of the variables that go into the relationships themselves, just the errors. So if you have data that look like this, you can use them in regression. You just have to check the residuals to make sure that the residuals don't look like this too. And if the residuals do look like this, it means that you're introducing additional error into your model. And so you have to interpret your results with caution. More studies are needed. All right. Now, another way that this can be violated is with the outliers. Outliers being one or more atypical data points that don't fit well with the data that you do have. Now, outliers can actually be really informative, sort of descriptively, qualitatively perspective. There's a really cool story in your book about the hole in the ozone layer, which was discovered. Wait, are you guys like old enough to know what the hole in the ozone layer is? Do we still talk about that? Okay, cool. So they discovered that hole in the ozone because they kept looking at scatter plots of their data and going, what is this over here? Something must be wrong with our instruments. And then they said, oh no, there's nothing wrong with our instruments. There's a hole in the ozone layer. Woo. But they can be very misleading if they are incorrect, because they can have a strong influence on the observed relationships with your data. Now, deciding what to do with an outlier is a discussion you need to have with your respective advisors and your dissertation committees, because it's kind of like a moral choice. Every field has a different way of dealing with outliers, but everybody will detect them in essentially the same way. So I'll talk about detection, and I'll talk a little bit about some of the options for what to do with them. But ultimately, that decision you have to sort of justify based on your field. Now, once you've detected the outliers, you need to determine why they exist. Maybe they're there because there's a hole in the ozone layer, and it's real, and it's a real problem, and you need to look at it. But they also could be, say, a coding error. Maybe somebody typed 112 and they were supposed to type 12. That's a problem. Check and see if it's a coding error. See if it's an impossible value. Maybe your range on the scale goes from 1 to 5 and somebody is coded as a 7. Something's wrong there. That person should not have a 7. Does it represent someone of a different population? I'll give you an example of what that looks like here in just a second. If the answer to all 3 of these is no, then it's something that I didn't write the rest of. If the answer to all 3 of these is no, then it's an outlier that you need to deal with sort of conceptually. So this is a true person from the population I'm interested in studying. It's not an impossible value. It's not a coding error. So what do I do with it? Then it's something to think about. All right, so how are we going to identify outliers? Let's see. You identify them as part of examining the residuals. If you notice, all of the assumptions are really about the residuals that you have in the model. So it's like, what's left over? We're really interested in error here in regression land. So we have residual diagnostics is the looking at something to see how well it's doing, specifically the error in the regression model. And I'm going to use this example, number of publications predicted from PhD, to show you how this works. I believe I put this data set on Carmen, so you can read along with me in your book. So you can follow along if you want to. All right. So a residual is the actual or observed Y value subtracted from the predicted Y value. And a residual plot is a scatter plot of the residual values with the predicted values. So as the prediction gets better, the residuals should get closer to 0. But before we can have residuals, we have to plot a line. Does that make sense? We can't look at the expected value if we don't have an expected value yet. So the first thing we're going to do is graph one of those. We'll do that by looking at years from PhD, which is our time variable, and publications, which is our pubs variable. And here we go. Here is our relationship between number of publications and years from PhD. Immediately, what do you notice? Case number 6. Way up here. This is all kinds of outliers. Here is the line of best fit to this data. Our seasoned faculty member, yes. The guy who just didn't want to publish. Precisely. This is that line of best fit here to this scatter plot of points. If you look at this line, you will say this is not very representative of the data that we see here. These residuals are going to be real big. Look at how big those are. Good gracious. What is your amount of error in this model going to look like? Is it going to be little or is it going to be big? It's going to be very high. It's going to be very large. Oh, okay. So just from looking at that scatter plot, we can see that case 6 is probably an outlier. But let's look at how it performs within this regression equation. We do it by examining the standardized residuals from the regression equation. And we'll do that by looking at the distribution of them first. So what I'm going to get here is a histogram of the residuals. Remember, for residuals, we want to have a mean of 0, which we'll always have by definition. And we want to have a relatively normal distribution of residuals. So here is our histogram of residuals. I'm going to back up and remind you what those residuals are. This is a residual. This is a residual. This is a residual. So I'm harvesting those residuals and I'm plotting them in a histogram. So we have nobody who has a really, really small two standard deviations below the mean residual. Nobody who has a really, really large 2 standard deviations above the mean residual. It's not really normal, but it's not really, it's just kind of weird looking. Nothing immediately looking at this tells me something is strange happening. So it's not coming out in that residual diagnostics so far. So the next piece of residual diagnostics we want to look at is how well we're predicting the outcome based on Y. Remember, we want to not have a heteroscedastic relationship. So we want to make sure that the error is not dependent on where you are on Y. Sometimes this is called the Y by Y hat scatter plot, or it's the observed by expected scatter plot. So thinking about this observed by expected scatter plot, I'm going to set a timer here for about 3 minutes. We're not going to discuss because I want to get to the end of this today. But we're going to let you think about it alone. What is an expected score in regression? What's an observed score in regression? And what do you want to see when you plot the observed score by the expected score? Shoot. Okay. I asked you to type it into the chat and then I quickly lost track of everyone. So I'm going to, who's somebody who answered? Abby answered in the chat a little bit here. What's an expected score, Abby?
An expected score would be something that's based on prior data, would be like something that would make sense to be an outcome.
Not quite. In this case, our expected
Oh,
score,
in this case, okay.
which, well, hold on. How about this? What's an observed score?
One that you measured.
One that you measured. Can I have someone go in for the Jeopardy steal on what an expected score is?
Whatever lies on that line.
Yes. Yes, Madeline. Where are you? Oh, there you are. Can you say yours out loud?
So yeah, our expected score is going to be whatever we think the score should be based on the regression equation. So we use the observed data to give us a regression equation, and then that equation will give us our expected scores.
Right, and it's observed minus expected that gives us the residual, or the opposite. And so what would I want to see if my prediction was really good? If I had sorted my X variables in one column and then sorted my Y variables and then I put them together, what would my observed by expected plot look like? Nina, go ahead.
If you made absolutely perfect predictions, they would lie, I think, on the same line. Like there would be no residuals. Every single observed point would be what you expected it to be. However, that's not really likely. So if you did like the sorting thing, you would just find very small residuals if your prediction was really good. And most observed results would be fairly close to what was predicted.
So if you have an observed score, an expected score of 7, your observed score is going to be also 7.
Yes.
If you have a really good observed by expected, if you have a really good prediction. So you would expect to see something like that example plot I showed you where all of the lines goes like this. If you've done a perfect job of predicting your estimate. So good thinking on that one. Yes.
That's a question.
Uh-huh.
Is that what you see usually when someone puts up like a graph, and let's say there's a line that's like the regression line, and then around it you have what looks kind of like a straw, like it just kind of like there's like a line surrounding it. I think it's kind of like, it's not like individual error bars, it looks like an error tube that goes around your actual regression line. Do you know what I'm talking about?
Yeah, those are confidence intervals around your regression line.
So that's not the same thing as residuals?
It is not the same thing as the residuals, but that's about the precision of your estimate, essentially. Okay. So not quite, it's not quite the same as this. Here we're talking about using the residuals to determine whether the model fits well. So those are two slightly different concepts. So here I'll show you what one of these looks like. In our observed by expected plot, look at this. Here's my predicted value on this x-axis. Here's my observed value on the y-axis. This is a terrible plot. We have done nothing. There's no relationship here. We would prefer to see one that looks like that fake thing where just as one goes up, the other one goes up. It's perfect. And we don't see that here. I'll show you a good one in a minute. I expect it to be a 5, give or take a little. Well, that is what the expected score is, yes. So we're not seeing that strong relationship here at all. There's a basically 0 relationship between the observed and expected values, which is not good. It means our regression model is not doing a good job. So in order to determine if something is an outlier, you can calculate something called leverage. Now, an observation that has leverage is an observation that has an extreme value on one predictor, but also has a lot of influence on the relationship. You calculate leverage following this formula, but you will never have to do it because it will do it for you, but that's the formula in case you ever need it. If you have a variable that has high leverage and a large residual, then it's very influential. But if it has just high leverage, we're not worried about it. If it has just a high residual, we're not necessarily worried about it. I'll show you what that means. So in this plot here, we have the residual for the model, the residual variables. Remember, that's just on average how far each point is away from the predicted line. Here are people who we got just right because their residual is 0. These people we have done not as good of a job estimating here. Here's the lower end of the residual. Now here, we have this point that has a very strong leverage and a very big residual. That's probably case number 6. Here, for example, is a big residual, but it does not have a high leverage, so we're not worried about it. We're really only worried about cases that have both a big influence on the model and a big residual. So you might be asking the question of like, what's a big residual? There's a table and a formula for calculating whether something is big enough residual to use. But if you have a plot that looks like this is pretty obviously a residual. I mean, a big residual. But in order to determine if it's has extreme leverage, this is the equation for identifying just how extreme is extreme enough to be worried about. So you calculate it using the number of cases and the number of predictors in your model. And so for 15 cases, we're looking at a leverage of 0.04 or 0.4 being the cutoff. And here our leverage is 0.8. And that's much bigger than 0.4. So we think this is an outlier who has a large residual. So this is something we've identified it. We need to look at it and figure out what's going on with this variable. Does it make sense to keep in the model because it's making a huge influence on the relationships that we're trying to estimate. So basically, if we're going to look for outliers, we are going to plot a line predicting y from x. We're going to look at the histogram of the residuals. Then we're going to plot the value of y against the predicted value of y. And then we'll plot the leverage by residuals to look for extremes. If you decide you do have an outlier, if you've done this like we've just done, and you find an outlier, what do you do? Well, there's 2 basic schools of thought. The first one is you can do something called bringing the outlier to the fence, which is just taking the very extreme value and putting it at the maximum that you see in your data set. Like, we know this person has a really big value, but it's so big right now, it's screwing with our estimates. So we're going to just pretend like they're only this extreme. In some places, that's very common. The other thing you can do is you can delete the entire case, or you can make the data just for this point be missing. So, for example, with our person, case number 6, we could just delete case number 6 entirely from our data set, or we could delete just the outlying value from the data set. If you do that, though, you need to do 2 things. First, you have to write about it in your paper. You have to explain what you eliminated and why. And second, you will want to do it again to check and make sure that you've solved the problem. So let's do that in this example. Here is that regression coefficient that I've already showed you, which is the regression coefficient with this outlier in the model. This is the regression with that outlier not in the model. That's a really huge difference. And just to show you the differences between the without the outlier and with the outlier, look at the differences here. I'm going to give you a second. Start typing them in chat, what you see that's different. Patrick, can I get you to talk about the slope that you noticed, the difference in slope you noticed?
Yeah, in the B weights, it went from negative 0.06 to 1.98.
Quite different. So if we're talking about remembering that B1 is publications years and publications, right? Is that what it was? Years and publications. Here, there's no relationship. Every additional year, there's no more publications. But what about here? Every additional year here, we're talking about 2 more publications on average. Yes, I saw R squared changed. Abby, can you talk a little bit about why the intercept changed? Why do you think that intercept changed?
Potentially because the slope of the line overall has gone from essentially 0 to pretty, like you're going up by almost 2. And so your the line itself has changed significantly. And so where that line is going to cross, your intercept is going to be lower when the slope is more positive.
Yeah. Yeah, that makes a lot of sense. And Jihoon, I see you're talking about the R squared. Why did the R squared change?
Yes, now, so as you can see for the model without outlier, R squared is 0.43, but outlier included is 0.004. So it was changed from 0.4% to almost 43%, variance explained. So maybe now we can predict more precisely.
Yeah, exactly.
Yeah, and the predictor is more meaningful for us. So it was changed, I guess.
Mm-hmm. Exactly. It's much more meaningful now. So I'm going to walk through the rest of this again, and then I have other questions for you. So in this instance, we have number of years is significantly predictive of publications, but here it's not. You just pointed this out, Jihoon, which is 43% versus 0.4%. Our slope changed dramatically, which we just said. So this is an instance in which, I'm going to go back to the graph. This is an instance in which with an outlier in the model, we do no longer see a significant relationship. Can you imagine a case in which the opposite might be true? Let's look at here's an instance where I have no relationship in my data. And I don't know if you can you see this? It's really small. Well, I don't have no relationship. My Pearson correlation here is 0.06. Isn't this awesome? I love it. And look at what it does. It spits out the data for you. So you can save it and analyze it later. So here I have 19 dots that I've made. The Pearson correlation here is 0.06. There's like no relationship here. But now let's say I have an outlying point. Look at this. Look what happened to my Pearson correlation. It went up to 0.40 with just this one person. 0.4, I know. And what if I add one way down here? Now it's almost 0.5. Let's do one more, which is like, here's where everybody is. I've got everybody down here. Observed. I have a 0 correlation. And again, now here's a very extreme outlier way up here. 0.83 is the correlation now. So if you remember at the very beginning of this section, I said that typically when you're introducing more error into your model and you're violating assumptions, you're less likely to see a significant effect if one really exists. But the opposite can be true for outliers. So in this case, you would see a significant relationship between your X and your Y variable, but it turns out it's just this one person, place, or thing, which is why we want to check. Okay, so just I have a little conveniently listed 7-step process for you to follow as you think about doing this in your own data. The optional homework assignment, which I'll put up next week, will be about looking at these regression diagnostics within your own data, which I would love to see you do, but you do not have to. And then before I go, I want to do one more walkthrough, which I have a data set here, and I have, come here, the steps that I just walked through with you in that example data here. So here I have an imaginary data set of Ohio State fans that have filled out my imaginary survey. And I have a question that I've asked them of how often they watch sports. And I'm asking them also how often they watch Ohio State football games. Just guessing, is there going to be a relationship there? These are not real data. I faked them. But still. So let's first look at the histograms of each, just to look for outliers. So I'm going to run this on Ohio Y. Hang on one second. Where'd my output file go? Here it is. Okay, there's my histogram of my Y variables. That's normal-ish, not exactly normal, but kind of normal. I'm not worried about that. Now I'm going to run it on my X variables. And it looks like I have a little bit of an outlier over here. It's almost like I made the data up. All right, so let's first look at the residuals. Well, I'll tell you what the correlation is between these two things next. The correlation here is about 0.6. So there's some sort of relationship here. So it's a positive relationship. So here's the syntax that I use to get the residuals regression, the residuals histogram. And remember, the residuals are the distance between the observed and expected. And I'm going to plot them all. Sort of generally, just to check our regression coefficient here, generally we do have a significant relationship between X and Y. It's positive, just like you all expected. Here are our residuals. I would be very happy to upload the syntax. I will do that right afterwards. So here's our residuals. You'll see that we've got this little guy way down here, but everyone else is looking really nice. It's a beautiful distribution, honestly. It's quite nice. So now we didn't see any outliers. So let's look at the leverage plot. Here's the statistics, the code to get us our leverage plot. And here's the one right up here that tells us there's something weird going on. Something funky is happening here. This person's not in the right spot. They are having a large influence on our data, on our relationship. So they don't belong. So then the next thing I have for you to do is to look at your multivariate outlier. So let's look at the scatter plot between these two. Yes. I can tell you're laughing. All right, so you can find the outlier in here pretty easily. Here it is down here. The rest of it is here. I really wanted to make the dot be the outlier, but I couldn't make it work. So in case you wondered, the relationship of script Ohio is 0.6. All right, so there's the outlier. It's got a pretty extreme value on X and a little bit of an extreme value on Y. And so let's look at the observed by expected scatter plot to see what that looks like. You just get it right there. Observed by expected. You can see that there's something going on here that's not quite right. So in order to next do this analysis, we can see what this would look like if we took this dot out. What's it going to look like if we take out this extreme value? You're right. Maybe that's the pit. You know, if you do the axis right, that's just going to be somebody in the pit. They're on the vibraphone. So if we take that point out, which I'm going to do by hand because I can't remember the code. Okay, they're gone now. So now let's look at these histograms. That looks normal. That looks normal. Isn't it terrifying what your data can look like if you don't check? Somebody just did a study on this, actually. Oh, it's so interesting. I'll have to find it and send it to you. All right. My correlation is now 0.7. It's a little bit stronger than it was before. Remember last time it was like 0.5? Now it's 0.7. And now what I've done, the next step I did was to look at the residuals. What did I do next? I should have gotten standardized residuals. So those look very normal. So this is also fine. And now looking at leverage, our leverage plot looks totally fine. These are all, nothing has a really big leverage and a big residual. So nothing is bothering us there. Okay. And now when we graph this, that person's gone. Ta-da! Okay, so I'm going to upload this syntax so you have it, but also you'll get an opportunity to work on this. I think we'll have to take a little poll because you have two options for lab this week. The first option is you can just have independent time to keep working on your assignments. The second option is you can have a chance to practice on this syntax in a structured environment. So think about which one of those you'd like to do, and then I'll ask you, or I guess Susan will ask you at the beginning of class, which one you'd rather do, so that you can have the option. Sorry, Susan, I usually don't dictate what you do in class, but I just did. Sorry. Okay, we're going to talk more about these next week, so don't despair if it's still feeling a little bit fuzzy and unclear, because we'll talk a little bit more about it next week, and you'll have the opportunity to practice it also in that structured environment. Okay, other things besides, let's just leave this plot up so we can look at how fun it is. Someone got very lost. Bless them. Okay, then class dismissed, which I usually say in a silly tone, but this time I actually mean it. Class dismissed. See you later. We'll see you here same time next week. And come see me on Thursday if you have questions about or you'd like some feedback on your final project before the final project is due. Okay. Bye, everyone.
Thank you.
Welcome. Oh. Whoop. Let me stop this recording. If I can find the right button.